All right, think we're good to get going. All right, so welcome everyone back to MOSAIC. This is our second ever meeting, so good to see you all here. Today we are welcoming Kyle Hammer. So Kyle is in his final year as a PhD student at the University of Kentucky. He's working under the supervision of his advisor, Peter Hislop. Kyle is especially interested in eigenvalue statistics and random Schrödinger operators. And I wasn't going to mention this, but since I came in the conversation I heard, I just have to throw in that Kyle is the one of the internet famous authors of the paper Skateboard Tricks and Topological Flips. I think I have that right.
Yep, that's
Uh,
correct.
so feel free to go ahead and look that up. It made its rounds on the internet when it first came out, is my understanding. Um, and then also, Kyle is, along with me, Kyle is a co-advisor for undergraduate research through the University of Kentucky Mathematics Lab, where we are currently working with our students who, I think at least one I saw pop into the room, we're working with them on coupled matrix population models. So without further ado, I welcome Kyle, who will be talking about computing critical energies for the one-dimensional discrete Anderson-Bernoulli model. All right, thank you,
Awesome.
Kyle.
Thank you, Ian. That was a great introduction. And indeed, yes, I am most well known for the skateboard tricks, but alas, I will be instead talking about things that involve the discrete Anderson-Bernoulli model. You can think of this instead rather as the discrete Schrödinger equation. So this is definitely something that, when I was preparing this talk, and as us mathematicians sometimes do, we love to be like, oh, look at the words and make sure the words are super perfect. I hopefully prepared this so that those words don't make sense. I will do my best to go through the slides in such a way that, sorry, bit of water, that this does not make any sense to you right now, but hopefully you'll have sort of an appreciation and understanding here at the end. So of course, we'll start off, do some background into what goes into this. And then I wanted to basically give you a story of how I got into it, which is not in the order that I'm giving this talk. And then actually talk about what is involved here, which is primarily this thing called the Lyapunov exponent. And then present this new result that I was working on that involves actually computing things with that. So a few disclaimers. I know this is a lot of words on the slide. This has the most words. Some of this background stuff on dynamical systems isn't in my undergraduate background. So I'm a little bit new to it in some capacity. I did a lot of things previously in number theory, topology, graph theory. And I did one project on mathematical modeling with PDEs, which ended up being my favorite. And I ended up going to graduate school for that, which is kind of funny. And then, of course, I had to mention, obviously, the skateboard tricks paper here, skateboard tricks and topological flips, as was mentioned, where we talk about that, in a certain level of topological classification, you actually get a group out of skateboard tricks, which is sort of interesting. And a little bit of a plug. If you want to hear about this, I'm more than happy to make slides on that. Just give me a little bit longer because I don't have them pre-made. Also, unfortunately, Overleaf changed their compile time in between the basis for these slides and, the talk I gave before and this one. And so I had to switch to the desktop version. And no matter what I tried, the bibliography just would not show up. So should you be interested in any references, I have them. I can give them to you. They just won't be in the references slide. I think it's blank last time I checked. So those are the disclaimers out of the way. So what is the actual point of this talk? Well, indeed, one of the big things was to give a PDE person's perspective on sort of interesting stuff that can happen with dynamical systems. So dynamical systems, they apply to pretty much everything. In particular, you can have things like with what Ian and I are doing for undergrads with populations. Of course, things like water flowing in a pipe. and as we will see, a discrete version of the 1D Schrödinger equation. And of course, these dynamical systems have two different types, continuous and discrete, and we will be strictly working with the discrete ones today. All right, so what do we need here? Well, what is the important things that go into this? Primarily a dynamical system, which is a system whose solution describes the time dependence of a point in space. So that is to say that you have two variables, a point in space and a time. And because you have a multivariable function where the solution u is usually some equation, pretty much always an equation, gives you some information. It's about interpreting that information that you get out of u. And one of the most interesting ones is fixing a point x and looking at the points in time. So you have a flow, which is fixing a point in x and then looking at the graph in time. And the graph is called a trajectory. Why do we need trajectories? One of the important things in the theory behind this is something called the Lyapunov exponent, which is something that measures the exponential rate of change of two very close trajectories. I have a visualization on the next slide. But the idea really is that if you go start off from two very close points, but they aren't quite equal, how do they change in time, right? How do they go out in time? And you can measure that rate of change with this lambda, which sort of, again, this e to the lambda t is that exponential behavior, where lambda itself is, of course, Lyapunov exponent because it goes in the exponent there. Okay. So this is a visual I got from Wikipedia. Sorry for the slight lack of quality. It's been, I took many screenshots of it, but the idea is basically that if you have two values, x naught and x naught plus epsilon, then if you take your solution function and iterate that many times, the question becomes how far are you away? And indeed, this lambda tells you how far away you are. So in fact, if you look at this equation after n iterations, you get this capital N lambda, and then again, the exponential nature, you could think about if you wanted to solve for that, you would need a natural log. And so just keep in mind that there's an n that we would want to get rid of to isolate it, as well as taking a log, and that's exactly what the definition is going to be in our case. So here's an interesting example of one of the things you can do with dynamical systems, which again, I'm about to show you some things that from what I've gathered haven't been computed before for the Schrödinger equation. Part of my interest in this talk was to figure out a use case for the pictures that I'm going to show you. So if anybody wants to do a deep dive into this, I'd be very interested to continue this. But the idea is to look at this thing called an orbit diagram. And basically, you can think of an orbit diagram as a graph of the long-term behavior of a dynamical system. And the very classic one is the logistic map, which has this form, xn plus 1 equals r, xn 1 minus xn, which in particular usually appears in like the study of, say, I think like rabbit populations is the common example. And so in particular, what you can find is based on the value of r, this equation is going to branch off into crazy directions. As you can see here, again, I could only save this picture as black and white from my MATLAB, but you get a lot of crazy behavior where all of a sudden you get this thing called a bifurcation, which splits out to two different values of x, and then it breaks off even further and breaks off even further. And then it breaks off to the point where there's basically no telling of what's going to happen, right? So at around this like 3.6-ish somewhere, 3.5 something maybe, I forget the exact value, you can see the behavior of your equation. So one of the things I did, surprisingly, was actually compute this for a couple of cases. So the rest of this talk is going to be about writing the discrete Schrödinger equation, or Schrödinger operators, same thing, and explain sort of an interesting phenomenon that happens in this equation that you can kind of see from these orbit diagrams. So from what I can gather here, I did the orbit diagrams for the equation we're going to look at, and you can see it looks quite a bit different, but that is, of course, because our variables are different. And so obviously things are a little bit strange here. What you'll find, though, that's quite interesting, is that the scale here is quite large. So the solution, right, each of those dots represents kind of a different part of the solution. And you can see that it likes to, of course, shrink down in little bits and then blow back up and so on at a very, very large scale. Don't worry about this repetitions. I will explain what that means shortly, but I just wanted to sort of show you that you can do this. And the full interpretation of what this means, again, is something I haven't quite figured out yet, but we'll get there. In particular, though, I did want to say it will be devoted to the question of what happens when we repeat something more than once. So that's going to be one of the key things. And again, if you look at the y-axis here, somehow when you increase the number of repetitions, for example, to 4, it does like to keep these waves a lot, closer together. And one of the things that you'll find is that, in fact, you do have these points that if you zoom in on them, they seem to all sort of collide into one, which is something that, although it may look like it with this scale, they don't do that in this other picture, whereas as I increase the repetition number, this happens more often. Again, I don't have a proof that it's exactly related to the thing I'm talking about, but we shall see. All right. So in the notation that we're going to be using, obviously time is in usually t as a real number. For us, we're going to use the letter E. This represents energy in the Schrödinger equation. For space, because it's discrete, we're not going to be working with continuous variables anymore. Instead, we're going to be focused on points. And any solution function will just be u at n, where u is some function from z into r. And again, our Lyapunov exponent will be denoted gamma instead of lambda. I wrote down the reason for that, actually. The people that started a lot of this investigation in the 70s used lambda instead of E as their time equivalent, and hence had to come up with a new letter, so they used gamma. And then all the papers after them, or their book and papers, used it as well in reference to them, and so it built on that. So it's a little bit weird for me after doing other dynamical system stuff, but that is sort of a relic of the 70s notation that they were using. Okay. So with this said, what are we going to be looking at? Well, it is the discrete Schrödinger operator. So the Schrödinger equation is one of the key equations in quantum mechanics, and is an eigenvalue equation with this operator H, which we will define shortly, on the space of square summable sequences. H itself has a kinetic energy part, which will be the discrete Laplacian, and a potential energy part, which will be a random function that we multiply by, which we'll see in a bit. And many of the ideas in studying this equation is to restrict to all of the integers in an interval, minus n to n, and then send n off to infinity to get a picture of the, whatever property you're studying on the full domain. Okay. So for any function that is in L2, we have this operator H0. This is our discrete Laplacian, or our kinetic energy, which has a very simple formula. It is just the sum of the two nearest neighbors of our point. So that is to say that if you want to define H0 of a function at the point 0, when j is 0, you would take the value of the function at 1 and the value of the function at -1 and add those together. It turns out that for those interested in the functional analysis, this operator is bounded, it is self-adjoint, and its eigenvalues, I put that in quotes. Again, you can have sort of continuous eigenvalues, which on Z, this is continuous, fills up -2 to 2 as our eigenvalues. So this is where things get interesting. So what I have been investigating, or did investigate with this project, is this. So for us, R is going to be bigger than or equal to 1. And anytime you see omega, just think that we're going to have some randomness here. And what we're going to have is a family of independent and identically distributed random variables with a common probability function. You don't have to worry about the measure part. Basically, the idea is that if I'm going to make a choice on my randomness, I'm going to choose my random variables, and then the choice that I make is going to not depend on what just happened. It'll instead, go again in the same process, right? So there's no dependence between any of those. And the identically distributed just means that, well, it'll be most interesting if I have this example. I went searching and I found this this coin here. And so you can think of it as like the coin flip, which is what we're going to be working with when you flip a coin, right? If you flip a coin again, your previous coin flip doesn't depend on it. You're flipping the same coin, which is the identically distributed. The independence is the fact that they don't depend. So what are we going to be doing with this? Well, we're going to have this v omega be a function such that I'm going to attach my random variable omega j onto r consecutive points. So in particular, you'd think about it as 0, 1, 2, r minus 1. So if when I flip this coin, and I don't know, I'll actually flip it live, and I landed on tails. So then I'll have a way to send tails to all of the points 0, 1, so on, all the way up to r minus 1. And we'll do this for any value of r, which will be quite interesting. So then our Schrödinger operator is going to be the function, or the operator h0 plus this v omega thing, right? And of course, it is quite interesting that the spectrum, or the eigenvalues, separate into two distinct things. The -2 to 2 is the one from h0, and this rho function, where did I put rho? Oh, maybe I didn't. Oh, that's my bad. Rho is the probability function. So the support of the probability function does get added on, and we'll see an example of that shortly. So how did I come across what we're going to be talking about? Well, as it turns out, my advisor, I was in a meeting with him, and we discussed this thing that he had been working on. And there was a theorem about the critical energies, which are the roots of this Lyapunov exponent. And he was showing me this result, and he wanted a way to figure out whether or not the result was true. And I asked him, Well, if we want to know to test it numerically, we're going to have to know some critical energies. And there was only one reference that he came up with. And so that's where I looked, and that is the basis for this. But it's sort of weird because if we restrict our operator h omega to an interval minus nn, and we take the eigenvalue differences close to a critical energy, then you're going to get this picture on the left here, which is that there's a spike away from the origin. And in fact, the thing that my advisor's proof did was find where that spike is, which is quite interesting. We don't have to get into it. It's a complicated, Schrödinger specific thing. But if you don't have a critical energy nearby and you take these differences, you end up with this nice exponential curve. Whereas if you have one of these, you get this spike. So this project started out with me sort of coding up in MATLAB. How do I get these spikes away from the origin, and where would I look to find them? Sort of a natural question. I think it's quite interesting. So what is known is that if this density function or the probability function is bounded, that's what this L infinity is, and R equals 1, that is to say there's no repeats, then you don't have any critical energies. The one example that we did have before this that I could find is that when R equals 2 and our random variables are Bernoulli, aka if your randomness is coming from a coin flip, then you do have these critical energies at these values v and negative v. So what this equation here is saying is basically that when you flip a coin, you assign heads to the value positive v, and you assign tails to the value negative v. Then it turns out that at those values, you get these so-called critical energies. So going back here, you would get a spike in the eigenvalue difference histogram. All right, so to go deeper into this, it's certainly quite interesting. We have this, PD specific thing, the Green's function. And the key point is this Lyapunov exponent gamma of E appears in the bound for this Green's function. So the Green's function solves a very important PDE for us, and instead it shows up in this bound. So certainly this is one of the ways that the PDE people discover this for the 1D equation, that they get this bound. And so gamma of E is called the Lyapunov exponent, and it controls this exponential rate of decay. And so the thing that I wanted to search for was examples where gamma of E was equal to 0. So we can take this equation that we have before, we can write it out in this format. And if you solve for u of j plus 1 in that equation, you can write it in this special matrix form, which you see now you get this matrix T of E comma j that is called the transfer matrix. And the reason that you do this is, in fact, the gamma v function is exactly what you would expect. If you know these things like I do, but this shows up all the time, right? These transfer matrices appear very often in the study of 1D Schrödinger equations, where indeed you have that 1 over n appearing to get rid of the n that we had before, and you have this natural log to try to isolate that gamma in that exponential. So if you take 1 over n and the log, and you take the norm of all of the transfer matrices, you end up with this gamma. So for the remainder of this talk, we will have our random variables have coin flips, and they will only take two values v and minus v. And so what's interesting is these critical energies are defined by transfer matrices commuting. And that'll be one of the things that we use here. So it's sort of interesting. The idea is that if the transfer matrices do commute, you can move them around however you like. And then, in fact, the only way that that can happen is if they have norm 1 and the log of 1 is 0, and that's how you get that. So let's look at the leading example here, which is this dimer model. And the idea is every 2 points, say 0, 1, and then 2, 3, and 4, 5, and so on, get the same coin flip value. So every pair of nodes, I flip a coin. Then I can actually combine the transfer matrices together, because at every 2 nodes, I need the same value. And so I can compute the powers of them. And you end up with things that look like this, which are quite a bit more interesting than the transfer matrix I put before. Oops, is that, yeah. And so the idea is that what Germinet and De Bièvre realized was that if you plug in the value v and minus v, on one side you get the identity matrix, which commutes with everything. And on the other side, you get this interesting other matrix here. And as it turns out, you can compute the eigenvalues and show that it has modulus 1. And because the identity commutes with everything, it's enough to show that when you plug in v, you do get 0. Okay. So I'm going to extend this and try to figure out how to get the identity matrix to appear in other examples. And is the identity matrix the only way to get these matrices to commute? Well, spoiler alert, it is. But what does all of that mean? When you extend this result to, instead of every pairs of nodes, you can have 3 and 4 and 5 and so on, then in fact, you do get that the critical energies, that should say plus or minus v there in the E crit part, apologies. But what you do in fact get is you get these new ones. And so if you plug in r equals 2 into this, you get k equals 1, and indeed cosine of pi over 2 is 0, which is where that comes from. So this result is consistent with the previous result of Germinet and De Bièvre. And the way to do this is to realize that if I want to study this problem, when I increase the number of nodes that get my random variables, I have to study basically this matrix. So before, I was ending up with either like a E minus V or an E plus V, and I don't really want to deal with the plus and minus issue, so I just sort of absorb it into this quantity alpha. Then what I can do is sort of define the rth power of them, which represents my number of repetitions. And the key result is this crazy lemma here that basically says that when I take the rth power of this matrix, we end up with polynomials in alpha. And if you take the equation here and do an induction, you end up with the following things, which aren't the most important. We'll see how they appear later. But the fact that you do have this minus of the off-diagonal terms, and that you have a factorization of the upper left component in terms of the others, in terms of smaller ones. And in particular, you know exactly what the degree is. So you get a degree r in the top left. The 2 off diagonals are degree r minus 1. And you get r minus 2 for the bottom right component. Okay. So with this, the thing that you can do that, again, this is the part that took like a page and a half, but you end up getting that you can commute these transfer matrices, the rth transfer matrix, at opposite values if and only if the 2-1 entries at their respective values give you 0. So it's a really sort of miracle thing that everything in the study of this, it turns out the only thing you ever need to care about is this 2-1 entry of this matrix. That holds the keys to the kingdom in a sense, because I get commuting. Commuting gives me critical energies. It all sort of works out. And so if we take a closer look at this, and the 6th condition, I apologize, it was like the 3rd one. I had more on there, but it didn't fit on the slide. You get this relation here, which it turns out is a changing of the Chebyshev polynomial recurrence, which actually, thankfully, had already been studied by people who did Fibonacci sequence stuff. And so, in fact, I found this paper on these Vieta polynomials, which is what they're called, thanks to this guy from Australia, A.F. Horodom or whatever. Again, sorry about the references. And he had this paper that investigated these polynomials and proved precisely that the roots of them are 2 cosine of k pi over r, where k goes from 1 to r minus 1. And so, in fact, because these are the values, right, I need to study the roots of this. I have the roots of them. I know what they are. I know that that makes it commute. That gives me a critical energy. You sort of trace it all the way back. And indeed, you get the set here. And the good news is it gives us exactly 2 times r minus 1 simple root critical energies that all live within the region that we care about, on which this whole entire problem is defined. And that's sort of the miracle here. I computed the values exactly depending on the value of r here, which I thought is quite interesting. So you can make your coin flips. You can assign them any value between 0 and 1 as long as they're opposite, and you'll know exactly what the critical energies are. My favorite is r equals 5, because it turns out one of the critical energies is the golden ratio. And so if we go all the way back to this picture here, to generate this picture in part A, I used that for r equals 5, the critical energy is at the golden ratio. So I took all the eigenvalues close to the golden ratio, and it turns out there's a spike there exactly as we predicted. So that was one of the things that I found interesting, is that the golden ratio is a critical energy of the 1D Schrödinger equation. Something that, you know, it seems to find its way in all of this math, but that is one of the cool takeaways from this. And I guess I might have gone a little bit over time, but as a final note, this graph here, for those that might be into combinatorics, gives you a poset of integer division. So the if you know what those words mean, basically what it means is every number that has 5 as a multiple is going to have the golden ratio as a critical energy, for example. So as it expands, it includes all of the previous multiples of every one of these integers as it expands out, which I thought was very interesting. And here's the broken references slide. Again, you can blame Overly for that. I apologize. All right. And with that, are there any questions?
Hi, Kyle.
Hello.
Yep. So I want to ask you a question on slide 15.
Yep.
I don't have the background to understand exactly what's going on. So I've noticed that V cannot be 1 over root 2.
Yes.
So what's so special about 1 over root 2? Because on other Schrödinger problems, I've seen, you know, one specific value a lot of times giving very specific behavior, like
Yes.
decay, for example, for a specific
Right.
value of parameters.
Yeah, so the V not being 1 over root 2, it comes down to, if I remember correctly, you can break these transfer matrices into I can't remember all of the titles, but you can break them into 3 different classes with their trace. Right? So the trace less than 2, trace equal to 2, trace greater than 2. And it turns out that in the case when r equals 2, if you plug in this v equals 1 over square root of 2, the trace ends up being exactly, and I can't remember which of the 3 scenarios it was. It's in this Germinet paper. But it ends up being the one value that I think gives it the trace equals 2, which is the thing that you have to avoid in order for this to work. All other values of v, I think if it's less than 1 over root 2, it's less than 2, and then you can do an analysis and everything's fine. If it's bigger than 1 over root 2, it's bigger, or smaller, I can't remember. And then everything's fine. And then this is the one value where they basically said the trace equals 2. That's not great for us because of this. And then they do this extra analysis there. So I can't remember the exact argument, but it does, I think, come down to a trace argument with those transfer matrices. Yeah, that is a weird condition.
Yeah. Also, I have another question, but I can ask in a moment if somebody else wants to ask something.
I do have a question. Could you go back to the pictures, to the, I don't know, the fancy pictures you showed us at the beginning?
Yeah, these ones, or
yeah. Could you describe what is happening here? What is like the x-axis and y-axis?
Yeah. Okay, so the x-axis is the value of E. So if we go ahead a little bit, how I did this was I basically wanted to iterate this equation through this matrix. And of course, I change the value of E, and then I look at the solution U at J, for example. And so what these fancy pictures are is that at that value of E, the question is all of the dots in each of the vertical lines is the solutions U at J that I found in, I think it's 50, J equals 50 to 100. So between 50 and 100, what does the equation look like when I apply it successively that many times? What is the equation doing? And the key thing I wanted to notice is that when you increase the number of repetitions, it actually sort of squishes this down, which is something I still haven't fully described or figured out how to describe. But when there's no repetitions, it ends up sort of very much sprawling out. Whereas when I have that value of R, which is our repetition number, when it increases, we end up having things that are very close together.
Gotcha. Another thing I wanted to ask is that it seems that you're looking for critical energies for which the Lyapunov exponent is 0, right?
Yes, it is 0.
So this should buy you continuous dependence on the initial data, let's say in these trajectories, right? Like the distance between trajectories should remain the same if your initial data is close.
Yeah.
What happens here with the extremes of this picture? It seems like everything is going like...
Yeah. So this comes into play because it turns out the eigenfunctions end up being these Chebyshev polynomials. And so if you like plot the Chebyshev polynomials and increase the value of n, what you're going to get is at the edges, you get these crazy oscillations. And I believe what I think is happening is that you get sort of this linear combination of those, and you're just sort of adding up all of the craziness of these out here at the edges, which is sort of interesting. It likes to keep it nice and contained in the middle, and then as you get to the edges of the eigenvalues, it just
So all of these illustrations are taken with the same initial data, let's say.
Same initial
okay,
conditions.
okay.
Yeah.
I see.
I should have clarified that. Thank you.
Have you tried to compare with different initial data to see if you are able to see this stability somehow?
Computationally, yes. Visually, no, because my poor computer, I'm doing this locally on my desktop, and having MATLAB generate this many number of points consistently is a little bit of a challenge.
That's
so
fair.
Indeed, changing the initial data at those values that I found, it's pretty clear that you're getting this nice stability, right, in the initial condition where everything else is changing. Graphically, I don't have the my poor graphics card doesn't compute it well, but this is something that I think will end up in my dissertation is the comparison here as a visualization. So I'm working on it.
Thank you.
Yeah.
Are there any other questions? All right, then if there are no other questions, I don't think there are, and I'm not seeing any in the chat. So let's give one final round of applause, if you will, for Kyle. Thank you, Kyle, for presenting today. Very nice talk, thank you. And then I will pass it off to Garrett for any final comments for our meeting today.
Yeah, I just want to thank everybody for showing up. I know we're still starting off here. This is just our second seminar, but I'm looking forward to us expanding. If you enjoyed this at all, or even if you didn't, I hope you consider like coming to other things. I really want, if any of you are interested at all in giving a talk, or you know someone who might be, like, please feel free to reach out to us. And I would really love it if we could try and get people from other departments as well. I just want to get, I want to gain a greater perspective of just what's actually out there and how can math be applied. So I think that would just be truly awesome, and I'd love to hear from you all. So yeah, just keep in touch with us, and we do have someone lined up for December already. So if you're on the mailing list already, you should hear about that. If you're not on the mailing list, head to our website or send me a chat right now, and I can get you the link if need be. But yeah, so thank you to everyone who was here today. So yeah, hope you all have a wonderful day.